1911, Hare and Marchson performed series of experiments under the direction of Rutherford that we call the Rutherford experiment, which led to the planetary model of the atom. So what was the experiment all about? So in the Rutherford experiment, what they did was they shoot some tiny particles at a thin sheet of gold. And what was expected? The expectation was that the atoms were like the pudding, with positive charge spread evenly throughout and with negatively charged electrons scattered inside, like the raisins in the pudding. But what happened was something different. When they shot these tiny particles at the gold foil that you can see in the middle, and they are shooting some alpha particles at the gold foil, it was expected that all of the particles would pass through the gold foil, and most of them did. They passed through in a straight line, but some of them bounced back. So what did this discovery mean? Some of the particles that bounced back were a huge surprise, and Rutherford, he realized that the atom was not like a puddle, but it had a small, dense, positively charged center, and it were the electrons that were orbiting around the center. And this was the experiment that revolutionized our understanding of the atom, because it led to the development of the nuclear model of the atom, where you have the nucleus as the central, the integral, and the dense part, and we say most of the atom is the empty space. Why? Because most of the alpha particles pass through the gold foil in a straight line, without any deviation, without any deflection, without getting bounced back. And that was the first experiment that laid the foundation for the modern atomic theory. In all of it, it happens in a vacuum chamber. So made up of small, just a recap, small particles called atoms. The atoms have a very small, very dense core called nucleus, and most of the mass of the atom is contained in the nucleus. And matter of fact, most of the atom is basically empty space. So let's take a look at the sample questions. So here we have the first one. A narrow beam of alpha particles is fired at a thin piece of gold foil, as in Rutherford's atomic model. Which is the final direction of the largest number of alpha particles? A, B, C, or D? What do you think? Okay, so let's check out this thing. Most particles passed undeviated. What does that mean? For most of them, there were no deflection whatsoever. They passed in a straight line as it is. without any deviation. So if most of them passed without any deviation, so we'll be getting A as the right answer, because they just go in a straight line, no deflection for any of them. And matter of fact, D is the one with smallest number of alpha particles. Only the smallest percentage would be deflected back or would be bounced back. A small percentage would be deviated, and even a smaller percentage would be bounced back. But most of them would be passed through without any deviation in a straight line. Okay, let's take a look at the next one. In the GM experiment, a beam of alpha particles is fired at a thin sheet of gold in a vacuum. The majority of the alpha particles pass straight through the sheet without being deflected. So you see, the answer to the first question is now given as a part of the statement of this question. And most of them pass through the sheet in a straight line without being deflected. This is now given as the statement in this question. What does this show? The alpha particle is uncharged. No, it doesn't give the information about the alpha particles themselves. The alpha particle is very large. No. It was supposed to give the information about the target, about the nucleus. The nucleus is positively charged. And the last one, the nucleus is very small. Okay, so the thing is, both of these statements are right. If we just take a look at these two statements independent of the question, then you'll be convinced to say that both of these statements are right, and they are. Nucleus is positively charged and the nucleus is very small. But we have to answer according to this statement that majority of the alpha particle pass through the sheet without being deflected, which means that the alpha particles were having plenty of free room, free space to pass through the atoms of the gold in the gold sheet, in a thin sheet of gold. So which means that the nucleus of the atom is very small, and that's why most of the alpha particles were able to pass through without any deflection. Only the alpha particles that hit the nucleus were deflected in different directions, and some of them were literally bounced back. So nucleus is a positively charged. That statement is true, but it is not true in this context. I mean, it does not give the information about this thing. So most of them pass through. It means most of the atom is free space, and thereby it implies that the nucleus, the central part of the atom, would be very small. Only then an atom can be mostly free space. So this question is very kind of a deceptive one. Alright, then we have the nuclide. A nuclide is just the representation of the structure of the atom. Each atom has a nucleus with a specific number of protons, and this is written as the symbol for the element, and on the bottom left side we write the number of protons or the atomic number. It can also be the number of electrons, because atom is electrically neutral, not magnetically neutral. It has a spin, but electrically the atom is neutral. On the top left corner we have the atomic mass or mass number, which is the number of protons plus the number of electrons. Number of protons plus the number of neutrons. So A equals number of protons plus the number of neutrons. And if you need to find the number of neutrons, you can just subtract these two. A minus C. An atom of one isotope of sodium contains 11 protons, 13 neutrons, and 11 electrons. State the nucleon number of this isotope. So what is the nucleon number? Nucleon number is basically this thing, atomic mass. It is also called nucleon number because in the nucleus we have mainly protons and neutrons. So that's why it is also called as nucleon number. So it would be 11 plus 13. Number of protons plus number of neutrons. So what do you get? You get 24. Explain why the number of protons is equal to the number of electrons in the neutral atom. Okay, or you can phrase it in a better way that the charge on proton is equal and opposite to the charge on electron, and hence they cancel out each other and the atom would be electrically neutral. A nucleus of this isotope undergoes a radioactive decay, not this one for the time being. Okay, then we have the next one. So it is represented by the symbol CO, which is cobalt. So the number of protons is 27, so can't be COD, and the number of neutrons would be the difference of these two, 59 and 27. We get 32. And for this one we can also add this thing, opposite in sign, not the spin, not opposite in spin, not in direction, but opposite in sign. For proton we have plus 1.6 into 10 to the power minus 19 coulombs. For electron we have negative sign, 1.6 into 10 to the power minus 19 coulombs. So proton number and nucleon number once again the same. Yeah, we can just complete this one. An atom of phosphorus is composed of 15 electrons, 17 neutrons, and 15 protons. For this atom, state the proton number. So easy one. Proton number is the number of proton numbers. The number of protons, which is 15. The nucleon number is the number of protons plus the number of neutrons. So 32. 15 plus 17. And the next part, the nuclear equation for this decay, we'd not be able to solve this one for a while. Okay, then this one, a small concept we studied, especially the chemistry students, they study this one a lot. Isotopes, the atoms with the same number of protons but different number of nucleon. So the difference in the nucleus is because of the number of neutrons. So let's move on straight to the questions. A nuclide has a notation X, 23, 48. Which line in the table describes a different isotope of this nuclide? So for different isotope, it must be having the same number of protons. So can't be B, can't be C, can't be D. It has to be the option A. Because isotopes, they must be having the same number of protons. Then we have the next one. The neutral atoms of all isotopes of the same element contains the same number of neutrons? No. Neutrons and protons? No. Any option with neutrons? A big no. Electrons and protons, because electrons, number of electrons and the number of protons in a neutral atom are equal. As a matter of fact, they are equal, and that's why the atom is neutral. Otherwise, it might be an ion, positively charged or negatively charged ion. Okay.